then.
Yeah.
Okay, so now we're starting to record. Okay, yeah, what was your question?
It's about relational algebra. I was just wondering, when you have two relations and one has a foreign key of an attribute in the other relation,
Yeah.
Do you still need to join them when you want to have an attribute that doesn't exist in the relation with the foreign key?
Yeah, I mean, you still need, the foreign key is there as a constraint over the state of the database. So it basically is saying that that if you add a tuple, it has to maintain what's called referential integrity. So if there's a foreign key, then, I mean, it can be a null potentially, but if it does actually have a value, that value has to be represented in the other table. But when you do relational algebra, you're going to need to treat it just like any other attribute to compute the joins.
I was also wondering if you want to check like a number or a count when you don't have attributes for it. Have we gone through that? If you want to check if something has,
we'll touch on that.
It's more than one or something. Okay.
We're going to touch on that today. Strictly speaking, it all depends on which relational algebra that you're using. We're using at least in the first recitation, you guys are using the classical relational algebra, which is based on set semantics and only has those operations, the projection, selection, union, set difference, and Cartesian product as a kind of the base. So the first recitation is over kind of the mathematically pure case. So you can't use any of the extended relational algebra operations. But in the second recitation, you will. So we'll hopefully that'll be clear. But you're using just the basic relational algebra in recitation 1.
Okay.
Right.
Thank you.
No problem. Are there any other questions that people have? Okay. So let's then continue here. So I guess everybody can see my new scheme here, right? There's my hand, and this is. Can people read that? Can people see this? I gotta get Good. Okay. So hopefully this will work better than, this is kind of just a webcam solution. But what's nice about it is it lets me use this guy, which is a lot more effective, I'm afraid, than the Scribble board. Scribble board is kind of there's some. It's maybe I can rig it up. I mean, it's not really that relevant. I think it has its uses, but I don't. I think this kind of more document cam setup here I have is I think going to be better. But we'll see. All right. So today, so again, last time we covered relational algebra and tuple calculus in their basic sense. And so today what we're going to do is we're going to get into SQL. We're going to show kind of the SQL, and those are, SQL is strong enough to express the tuple calculus and the relational algebra. And what we'll focus on right now is just getting a good correspondence between those. But then as you see, what we're going to do is we're going to extend the relational algebra at least, and we're going to, in fact, we're just going to kind of leave the tuple calculus and go over to SQL instead. So SQL is kind of, so the relational algebra, when we get practical, it becomes the extended relational algebra. And the tuple calculus, when we get practical, becomes SQL. All right. And then there's a lot more other stuff that's added in. So we're going to just introduce you guys to SQL today. So we're just going to basically have these select from where statements and multi-relation queries. And I guess some of you have already done SQL stuff. So, okay. So why SQL? SQL is a very high level language that allows you to do declarative statements like tuple calculus, which basically tells you what you want. It says, you specify what you want rather than how to obtain it. SQL is so there's another option, of course. I mean, if you think about it, just kind of conceptually, if you say, well, why do I even want a query language? Instead, what I want is I just want a data structure, and I want a program. I just want to write programs that access the data. They just go in there and loop over things and kind of go in there and actually, I can do anything with a programming language. So why don't I just write my queries in a programming language? So basically, why don't we just have this giant table structure, and then I'll just write like a Python function or set of functions or a whole system to go in there and to grab data, to do queries, right? So that's been tried, and it's very, very hard to maintain. And a lot of times it's actually, based on the debug cycle, it's actually less efficient to do things that way. It's nice to actually have a high level language. So a lot of these, the data, so like using C or Java or Python to go through and to actually grab data out of large structures is, there's a good reason why people don't do that. Then, of course, with SQL, there's the idea that the data, that the actual system itself does query optimization. So you basically just say what you want. So you say what you want, and then the idea is that the optimizer then will compute how it's actually, it will figure out how it's actually going to do that efficiently. So that's the argument, at least. If you right click on any of the participants, you can. Oh, I'm sorry. There was a question. Some people were helping each other. Okay. At least that's the thing. I mean, the question of course, I mean, really, when it comes down to it, is this really true? We're going to come into what really goes on with query optimization. Sometimes it actually does help for you to actually have some knowledge when you actually specify what to do, because these query optimizers are not omniscient. So sometimes it actually does help to know to make things more efficient. So the way you say it here sometimes will result in a efficient query plan from the query optimizer. But if you say it in the wrong way, then it doesn't really know what to do, and it'll give you an inefficient one, right? So that's just the reality of it. All right. So SQL is basically, you could say that basically SQL is the tuple calculus plus the relational algebra. So you can do both, plus a lot more. So it has aspects of the tuple calculus in that it has these tuple variables. It has no universal quantifier, so there is no quantifier that. But instead, it simulates that with a double not exist, and we'll show that later on. All specs, yeah. So it has all the relational algebra operators, and then it's made. It's of course it's made practical with it has a bag semantics, and then of course it has updates, and then it has real data types. So we really haven't specified data types in our relational algebra or tuple calculus, but there's a notion of data types. So in other words, well, there aren't that many really distinct data types, but well, there are a lot of distinct data types based on the SQL dialect. But there's things like, if you think about it, there's like real numbers, there's integers, there's strings, there are clobs. So there's something called a clob, and there's something called a blob. So you have clobs and blobs. So a clob, that's a character large object. So that could be like a clob could be just a gigantic, like a whole book could be a clob, right? All the text in a book. The title could just be a string, right? Or varchar, a string, but the actual content could be a big clob. And then a blob, that could be something like an image or something, right? Or a movie or whatever. A blob is just a binary large object. All right, so we have more rich data types in SQL than we had. We don't even talk about data types in tuple calculus or relational algebra. So SQL will give us that as well. Then there's a whole bunch of other things that we'll get to, arithmetic, aggregation, recursion, but we'll cover this later on. I don't want to get too much into that right now. And there's a lot of built-in functions. All right, and of course, this is all based on what dialect of SQL you're using. That is what system you're using. But the idea that there's kind of a core of SQL that is common among them all, so you can facilitate basically. You can wind up using one SQL engine like MySQL for a long time, and then you can wind up saying, no, I want to go over to PostgreSQL, and you can migrate the data out of that in a kind of a more, using kind of the standard SQL, like the core standard that everybody follows. All right, so you'll see these terms right here, the DDL, the data definition language, and the data manipulation language. So the definition language is where we actually define like the tables, and the manipulation is where we do the updates, inserts, and selects and deletes. Okay, so I hope that's clear. All right, so we're going to do some examples here. So we're going to go to actually the screen here and just kind of show how we can do this. We're going to do this on the computer, and we're going to use the example called the Northwind example, which I'll show in a second here. And these are, you can download these from the reading site, and they give you so everything that I'm going to be showing you right now, you can actually download yourself and do. And you might want to. All right, so let's first of all look at this Northwind schema. I hope you guys can read this. All right, so we have the notion. It's basically the idea here is this Northwind is like some food distributor. So they have customers, they have products, and they have suppliers, and they like drop ship stuff. I get, or they have a store or something maybe, but I think they actually no, I think they are a drop shipper. So they drop ship products in these big orders to different customers. So if we look here, what we have here, this is kind of a oh wait, one sec. So I'm sorry. I just see something going on in the chat here. Okay. Well, can people see this right here at least? I mean, can people? I'm not really sure how much you guys can read on the screen. Can people read this? It says suppliers there. You probably can't, right? No. Yeah. So that's it. Okay. So all right. How about this? Can you guys read it now? Can you see it now? Almost, kinda. How about now? Oh, God. All right. So there's suppliers, but let's start with something. Let's just start with something really simple here. Let's start with products. So you see the products there? Kind of. I mean, if you guys download, I mean, this isn't this. Yeah. I wonder if I can. No, I don't dare hit that button there. I don't know what it does. I think there's a better way for me to show this. Now, when you go to the slides, if you can bring up the slides, you can see this. This is just a simple diagram that's showing kind of the well, the tables. We have 1, 2, 3, 4, 5, 6, 7, 8 tables, and we have these primary keys here that are specified. So if you look at if you get the slides, you can actually see it, but it's not really that important that you do that at this point. Let's instead go to the following. I'm going to share a different screen here, and the screen I'm going to share is la-di-da, share. All right, now can people see that? All right, very good, very good. Okay, so what you'll see here then is that here's the, if I go to this Northwind SQL, there it is. All right, now people, now how's this? I mean, can people read this? Yep. Can people see this as customers here? All right, good. Very good. All right, so this actually is the SQL that's going to define that Northwind schema. So I said what I said, there was 8 tables, right? So there's 1, 2, 3, 4, 5, 6, 7, 8. Good. That would have been embarrassing if there was 9. But there was 8. All right. So those correspond exactly to the diagram. But let's look a little closer here at what's going on here. So let's start with an easier one here. Let's look at products. Okay, there's a product. All right. So a product has an ID, and then it has a name. And if you notice here, this is where the types are being defined. So this is SQL, using SQL as a data definition language here. So we're using it as a DDL. All right. So we have the products, then we have the supplier ID. So that's the supplier who supplies that product. And notice here we have this thing where we're saying references suppliers. All right. Now what this is don't worry about deferrable for right now. Right now, what this is doing then, this is saying there's a foreign key. So basically what it's saying is that in any kind of products table, or tuple rather, so a tuple, or you want to say a row of a product, if it's got a value here, it's got to reference the actual, an actual supplier, right? And same with a category. So it's like the category of the product. Then we have the quantity, we have the price, et cetera, et cetera. All right, like we have stock. There's some various numbers here that we have. So if we look here, let's look at suppliers and categories. So if we look here, there's suppliers right there. And notice here, a supplier has a primary key, all right? So yeah, and it's an integer, right? So that's the constraint, it's a primary key constraint. So again, if you have a tuple here and there winds up being a number for the supplier, then it had better be a tuple in the supplier table, right? That's what a foreign key means, right? Now, if we go up to categories, then we'll see also we have categories here. So what's happened here is the links, like the foreign key constraints that were in the diagram, are all being defined by basically this reference is a keyword. So right here, if we look at orders, so the orders have to reference a customer, right? So it's because there's a customer making the order. All right. Then we have order details, and they're going to reference an actual order ID, right? And in this case here, they can't be null, so you can't have an empty. So it's got an order detail only makes sense if it's referencing an order. Order details only makes sense if it's referencing an actual order. And notice here, the primary key here winds up being two attributes, because an order detail is an order and then a product, right? Those together. So you might have, for like one order, you might have 7 tuples in the order details, right? Of all the different things that went into the order. Maybe I got, we'll see there's various products that we can have here. All right, now what we have down here is we have actually the thing that's going to build up the database, right? These are the actual insert statements that are going to build up the database, right? So we have beverages, condiments. We have the basic categories here, and then we're going to wind up having all the other stuff here as well. So let's just go back here then, and let's do the following. Let's just say, so now this is PostgreSQL, and I always think, well, it'd be great if you guys actually just would download and you would install your own PostgreSQL. It's kind of a good exercise for you guys to be able to do that. I think that's my opinion. But some of you guys are actually going to wind up just getting support. You're going to use that one support gave you. That's fine. So I'm going to basically do this. I'm going to say create DB, and I'm going to call it Northwind. Okay, so now I've created DB. So if I basically say that, if I say PSQL Northwind, and I go in here, now there's no relation. So the whole thing's empty, of course. So if I go back out here now, and I basically say this, I say, okay, Northwind, and I say, I want to load in the file, and what was it called? Northwind SQL. Okay. So now what it's doing, there come some problems that I had with the data set, but don't worry too much about it. It has to do with some of the things that were breaking the foreign key referential integrity. So some of those tuples didn't get added. But now, if we look at this, we go in here, and now I go backslash the DT from this is a PostgreSQL idiosyncrasy or syntax or special system commands, just to kind of list the tables. MySQL has its own way of doing, like the show database or show tables, and all the different variations have different ways that you can kind of do this stuff. Notice how I do not use pgadmin. I'm not really a big fan of pgadmin. I like to do things from the command line with PostgreSQL. All right, so what are we going to do now? All right, fine. So this shows that we've just built a database. So we just built this thing from scratch, right, based on that definition file. All right, so now let's get back to doing some querying. Let's talk about, talking about kind of the point at hand here, which is this, let's start with the relational algebra. All right, so I'm going to show the SQL that corresponds to the basic relational algebra statement. So if we wanted to project city from employee under the set semantics, and that's why this distinct is here, right? Because remember, SQL is a bag semantics, and I'm going to force it into being a set semantics by using distinct here. But what I'm going to do is I'm just going to grab this guy. I'm going to do this with control copy. And then I'm going to paste her in. And let's see what this is going to do. So this is going to give us the distinct cities from the employee table. Ah, there we are. So Redmond, London, Tacoma, Kirkland, and Seattle. So if I say this right here, select star, this will just list me, this will just give me the full table for employees. It's a biggie. It's kind of broad there. Here's another. So it's got basically what it has employee ID, last name, first name, title, blah, 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 blah. And if we notice that we have city. So I just want to project out the city. All right. So that was the relational algebra expression I was doing there. So select distinct city from employee. Right. Okay. Now, if I go here and I get rid of the distinct, this will give us this is what it's coming back as a bag semantics now. So now you see London got 4 times. There are 4 Londons there. So a lot of people working in London. I wonder if that's London, Ontario, or London, UK. All right. Well, is it country? Is it Canada? Because there's a London, I guess it was country, right? Okay, it's the UK. So it's in the United Kingdom. It's the big London. I guess there's another one called Londonderry, but that's different because it's got Londonderry in the name. There we are. That's the projection of two attributes, right? Of course, let's get back to set semantics. And there we are. So the distinct covers the whole, all the combinations, right? So it's not just over a single attribute, but it's over the pair of attributes there. All right. So that right there is going. That just showed us that we can do projection. Okay. So what's the next operator? We want to do selection. Oh, here's a selection. We're going to basically get all the products where the units in stock is greater than 100. Okay. I'm so used to doing it this way. Okay. So now, let's see, how many are there? There's 10 of those. So if I basically go back here and I basically say, well, let's just get all of them, then there's going to be 77. So 10 of them have more than 100 units in stock. Right? Okay, so that's just showing right here. This is showing, again, that right there is an equivalent to a selection, right? A relational algebra selection. All right, then. Okay, so now what's next then? We have, oops. What else do we have? What's the next one after selection? We have the Cartesian product. Okay, so with Cartesian product here, now notice here, I just want to show you guys one thing here. I'm renaming things here. I'm giving them what are called aliases. And it's good practice to try to alias a lot of your tables. One of the reasons that if you ever wind up doing a self-join, and you're going to wind up doing that quite a bit, you need to have distinct ways to reference the same table definition, but with distinct names. But anyways, here, just to kind of give us some good practice here, we're going to basically say select products as X. Okay, so then you would use X. So in this case here, I said as X, and then I said X dot units in stock. So that was a way to say, well, which one where was I putting the condition over? You know, if I had other products here, then we would need to have X or, you know, I mean, let's see here. Maybe I'll give an example of that soon, or maybe one will come up. All right, right here, this is a Cartesian product. And notice how the Cartesian product just pops out naturally based on just kind of the combination. We have here basically select distinct. So if we do this, right? So this is doing all the possible combinations. So Grabad locks is being paired with all the different categories. So is Grabad locks a dessert, candy, or sweetener? No, it won't be. So that's one of those meaningless kind of spurious tuples that a proper join will then wind up solving for. So, you know, it'll basically say, because the category ID of Grabad locks is probably corresponding to like meat and the seafood. I would imagine seafood. Grabad locks 17, seafood is 8 there. Yeah, I think this is the right here. This is in Grabad locks, this is the category ID, and seafood has the category 8. So 8 equals 8. 8 does not equal 7. 8 does not equal 6, etc., etc. So those ones won't make it in if you were doing a Cartesian product followed by a selection to pluck out the right ones. Of course, we'll see that we can just do a direct theta join later. All right, so if we look at that, I wanted to show just the kind of logic of this. 616 rows, and indeed, if we look, I think I have it commented here. If I say this, if I say select, now this is not a relational algebra. This is not relational algebra. Right, because we had no idea of how do we do counts. So if I look at the number of count the number of products, I got 77, and if I count the number of categories, I think it's 8 rather. I'm sorry. Yeah, and that's 616. So that just shows that the full Cartesian product is being calculated. All right, so let's continue on. All right, so this right here, if you want to, if this kind of makes you a little bit, you know, kind of queasy, because it's just kind of SQL just by its normal semantics is going and finding all the bindings and it's doing a Cartesian product. But if you want to actually say cross join, do it this way. I don't know how many people ever do this though. I mean, having the cross join. I mean, I would probably look askance if I saw this in someone's code. I would say, well, why don't you, do you understand? I mean, but it's there in the syntax. So this will give you the same things here. This is actually a bit better here. So natural join. Okay, so let's look at the signatures here. I say it's kind of unorthodox. I say when I say signature, what I mean is let's look at the actual. This is one way you can do it in PostgreSQL. If I say categories, it's got category ID here, right? And it's called name category ID, and the type is integer, right? And if I do the same thing with products, look here, it's got product ID, or I'm sorry, it's got category ID here, and it's type integer. So these are actually shared between the two tables, right? So that means that we can do a natural join as a candidate for a natural join, because the name is the same and the type is the same. So they should, natural join should work. So here, let's see here. Yeah, so if I do it this way, I do the natural join. So I think that each product has a single category. So this should actually give us out 66 results, right? All right. So, but yeah, so what it's doing here is this pairing. You see here, Chang is a beverage, I guess. That's definitely. I think I've actually had that. It wasn't bad. Yeah, 77. Okay. That's right, because there's 77 products. Let's just verify that. Another question? Yeah, good question. Very good question. What happens if they have multiple attributes that are of the same name and type, presumably? The natural join will do a natural join. So let's just. So of course, let's see here. If I basically say this, if I say, what other table other than? We know one thing here, that this table here, product that. All right, there's that. Distinct product name, natural join. So if I natural join it to itself, well, by definition, they have a lot of attributes that are in common, right? And it's distinct here. So this, I say this is it'll be embarrassing if it doesn't work. This will give us back the, what will this give us back? This will give us back, exactly. So what it's doing here is it's forcing equality on all of them. I hope people see that. So I'm doing natural join. These are, the products and attributes. So this is kind of pointless, but I think maybe it shows. So this should actually equal right here. This should equal the original product table. So if we go over here, yeah. So there. So that's just showing that natural join it really does check, and it does equality on all the ones that are the same name and same type. All right. All right. Here's the theta join. All right. So you might say something like this. You might say, so theta joins are going to be more common, actually. And the reason why theta joins are going to be more common are that, well, it's most of the time you'll have something like a lot of times it's not very good practice to have the same name attribute all over the place. You'd want to have ID, like the same name attribute ID on products and on customers and on everything. Because if you have this kind of that consistency, then it makes it a lot easier to kind of formulate queries. Oh, wait, let's say another question. Can you always assume that two attributes in two different relations are the same if the name and type are the same? No. In fact, you cannot. If you have a foreign key, then yeah, in a way you can. You would basically say that one is a subset of the other, right? And you can have multiple attribute foreign keys. We'll get to that later. But in general, no, you can't make, unless there's a constraint like a foreign key constraint. You can't make any statement. But you can do it with a foreign key. So yeah, so it's very flexible in that way. So it doesn't, but natural join, it doesn't really, it will do it. It will basically look is the same name and the same type, and there's two tables coming in. It's gonna force a natural join on it. All right, so it's gonna force equality on those. All right. Okay. So this is good. Yeah. If anybody has any more questions, just fire away. All right. Here's the theta join. This is not really my style, the way that it's being done here. I'll show you my style, but let's just take it here. So I'm kind of a minimalist in many ways, because, it's just kind of, what can I say? So right here, is there another way we can do this? All right, so let's say we have select. So first of all, what are we doing here? We're combining two things in relational algebra. We're doing a theta join here we're doing a projection off of a theta join between the products and the categories, right? So we're basically doing right here, we're saying that the category ID has to equal category ID. It'd be probably better to do this with a natural join, but if we look at this right here, let's look at it this way, because this will show us that the all right, this shows us here that the category ID here and category ID get replicated here. So it's a little bit, that's actually kind of interesting. I wonder what kind of problems that would cause now. SQL can be a little tricky in this regard. So what would happen now if I did a join on that with something else? If I took this table here and joined it, SQL would probably have a runtime error, PostgreSQL, because let's say I took this thing and then I try to do a join on category ID. It looks like it's replicated the attribute name here. So that's kind of that's going to cause problems potentially. But this is the full theta join. I mean, if I do a projection like the original query, that we won't have that, of course. Here's the theta join, but you see the category ID is replicated, right? Because it's doing a theta join. But by the way, I think the point I wanted to get to was the style in which I would do this thing is the following. I would basically just say, because I'm kind of a minimalist, I would say, who wants to use this on thing? That's kind of, I don't want that. I like this better. So this will make it a Cartesian product. So there we have a Cartesian product happening, right? Products, categories, and then it's doing the selection on top of that. So it's doing a Cartesian product and then applying a selection to that, right, to get the result. So then you might say, well, here I'm kind of getting ahead of myself, but since you guys are probably this yawning, saying, God, this is so basic. What is he doing? All right, explain, analyze, All right, so the execution time on that guy that's pretty fast, 0.142, and then I'm thinking this other one where we're using the actual theta join. Let's see if that one gives us better performance. Execution time is 0.243. It looks like it's so fast. There's a lot of variability there. The argument could be that using the theta join syntax could potentially be more efficient because it gives the query optimizer a bit more instructions. But I think in such a simple query like this, I think it's not going to make a difference. But sometimes you notice that explain analyze, that's what you trick around with to kind of get better performance. You want to do that. But in this case, since it's so fast, it probably just has to do with kind of like the reason why one runs faster than the other has to do with some other background processes that are running on my machine or something. So let's see. Let's continue on here. That was kind of a little bit of a getting beyond ourselves here. All right. So now we say natural join. So look at this right here. We say that was a theta join we had there. Here, this kind of is nice here where we say, what about this? So we're doing a bunch of natural joins. So the way they wrote this Northwind is it's kind of amenable based on the way they did the namings to doing natural joins. So this is going to be, what are the categories of products, which then also are supplied and that are supplied by somebody, because there's probably a product ID in the suppliers table and there's product ID in products. So this natural join makes sense all the way. And then there's the country of Sweden. So what are the categories of the products that are being supplied by Sweden? And we know it's going to be at least seafood, right? Because Gravad Lax is coming from Sweden. There it is. So grains and cereals and seafood. Right? And then let's take a look over here. What else do we have here? That was natural join across. This is the same one. Anyways. All right, let's see. Any other things to look at here? Okay, so I hope this is making sense for people. So now if we look at the set operations, so we're going to look at, so now, we've done Cartesian product, we've done select, project, and now what we want to do is we want to get the set operators in there to complete the relational algebra. So if we look at cities, so we get the city from suppliers, right? That's a table, right? Selecting cities from supplier. That's like just, the type is string and varchar. And we want to union that with the cities for the employees. So this is going to be the cities of the employees union the cities of the suppliers. All right. So we'll get to this later. It's kind of a quirk in SQL, but I keep on telling you guys that the SQL is bag semantics, but lo and behold, that's kind of not so nice. There's 33 of those. All right. Now this is getting beyond, but I want to do it. We don't have this in our basic relational algebra, in this like simple relational algebra. We have no sorting, but we're going to get it in the extended one. Anyways, there we are. So now, this, by the way, everybody, is my hometown, Ann Arbor. Ooh, the best. That's where I was raised. So, okay, 33 tuples. All right, so but now if we do this, we say this, union all. Now now London is getting replicated here. So this is a bag semantics. So this is kind of like doing the bag union. But what SQL does actually is it's kind of quirky, but when you say union, it takes it and brings it down to a set semantics. Right? And the reason why it does that is basically mostly because for it to do the calculation, it's going to wind up removing duplicates anyways. So it just kind of does that as an efficiency thing because it's going to do that in the set operations. If you want to overwrite that and get the bag out, then you basically say union all. So you need to add the all to get back bag semantics on the set operator. So it's a little quirk, but right now it's kind of going to be helpful for us because if we just do this, then we wind up getting our there's our union operator, and then we can maybe do instead of union, what else can we do? We can do except, which is the minus operator. Okay, so it's like give me these except. So if we look at we get the cities from the employees. What is this? Oh, from the supplier. So I'm doing it over a little different table here. Sure. Now I'm going to do it this way. I don't know why I didn't do it here, but maybe. Maybe because there's 28 now. And then what was there when the union? Okay, yeah. So there were some that dropped out. Okay, so that's except, and then so if we have union and we have except, then well we already have covered all of relational algebra because with those you can get intersection. But let's just for the sake of just keeping things full here, let's just do intersect. All right, is that it? It was only London. Huh. Okay, well we learned something today. Right. So that's set operators. Okay. So what else can we do? Okay. Now here's another thing we can do. So you remember how we were building up those kind of larger relational algebra expressions from kind of sub ones? We can do that also here in SQL. So we say select the Swedish product name, I guess, from, and then here's the new table. So this is a table right here. So let's just kind of show what is that table. This is going to be the table where we're getting all the Swedish products. It looks like. One sec. We're getting well the category name, the product name as a Swedish product. So this should be actually kind of interesting. Let's see here. I think Gravellock should be in here definitely. What happened there? Oh yeah, this is a common problem. So a lot of times students will do this. They'll put this in here. And accept all, I think. Except all will do it looks like there's a question here. Except all and accept. So except all will basically do the bag semantics of a difference. Okay. So that means that like if I have 7 in the one case of London's and I do a difference, and then I have 6, or let's say I have 7 Londons in the one set, and I do a difference, and there are 2 Londons in the one I'm doing the difference, and I'll get 5 Londons. Yeah, exactly. So the student saw that, well, but I just wanted to kind of do it like, so this will happen a lot. It's like, well, I just typed in my query. What's going on? This stupid thing. Yeah, you got to terminate it with a semicolon. Boink. All right, so there we are. These are going to be the category names with the Swedish product name. All right, so this defines a table, right? That's a table, that's a relation. So what's going on here is that we're putting all that under here, and we're giving it a name called Swedish products. And then from that, we're getting the product name. So I could do something like this. I could say something like this, if you really wanted to kind of get into it. Okay, where the category name is seafood. So if I basically say all right, so that should be. So it's going to bring out the full table here, and then it's going to do a select. So when I say select, so remember there's select. This is a project, and there's a little bit of a strange kind of what is it? When I say select, I'm talking about in relational algebra sense, but really it's a where clause. All right. So, anyways, this should give us just out the inlocked seal and the ground locks. Yeah. So just getting that right. So you see what's going on there. This thing's going to cough up that, and then it's going to go over that as a table, as its own kind of synthetic table that's being created inside the query, and it's going to basically say where does the category name equal seafood, and then it's going to pluck out those names, right? So the keyword select, yeah. So the keyword select, but the thing is that most of the time you guys are just going to, well, let's be honest here. I mean, probably in your future, work and all that, you're just going to forget the relational algebra. And you're going to think the project. You're going to think when you think select, you're going to think the SQL sense of select, which is project. Right? NVM. Oh, never mind. I guess. All right. Okay. Good. All right. Time. All right. So, anyways, that is kind of just showing that with SQL we can kind of trick around here. We can get with the relational algebra. Let's see, do I have, we're going to go to Tuple Calculus next. So the Tuple Calculus, we're going to do that. I think we'll just do that after, when we get back at 15 after. But we're going to do that. I don't think, we're not really that much in a rush because we actually have a fair bit of extra time kind of built into the course. But I know I'm going a little slow for people, but maybe it's better that I do it that way. I don't know. It's kind of better to kind of do it slow and steady, since we do actually have a fair bit of time. Okay, good. So people, yeah. I mean, I think I don't want to rush things. Don't worry. There'll be times in which things are going to get a little bit complicated, and then right now you might think this is trivial, simple. It is kind of simple, but we will be able to get to some kind of meatier stuff. We're building up to that. All right. Okay. So when we come back, we're going to do Tuple Calculus in SQL, and then we're going to talk a little bit about some of the extras in SQL, and then we're going to go back to the lecture slides. All right. So okay. So let's get back here at 15 after 11. All right. I guess I'll pause the record. Where is it? Where are you? Oh, I got to stop the share. The thing is, my document camera is blocking everything here. Okay. Stop share. I might actually kind of ruin everything. All right, I'm going to pause here. Okay. Oh, see, try there at 15 after.
Michael.
Oh, yeah.
I have a question.
Sure.
For the first, recitation and so, because I didn't really understand when you're using relational algebra.
Yeah.
How can you say that something has to be a minimum of I don't know, a number with only the basic?
Well, the thing I guess I should try to tell you that is that when we do select, here, I'm not going to do this inside of relational algebra, not the SQL select, but if I say something like this, if I say something like all right, if I say that I have, let's say, a product or something, and I have the ID and I have the price A, and I have price B, I can certainly do the following. I can basically say, all right, give me, I'm going to do a select over this, over P, where price A is less than price B. So some of these kind of built-in arithmetic kind of, well, arithmetic comparison, equal. So we have the kind of standard 6 kind of operators here. We have equal, not equal, less than, or greater than, less than or equal to, greater than or equal to. So all those 6 are available to in how you specify the condition here inside of a select.
Yeah, but in this case, could you in some way say that you need at least 2 products, if you get it?
Yeah, I get what you're getting at. The thing is, I don't really want to answer the question because I want you guys to kind of like, I mean, I'll give you a hint. The hint is basically, if you want to start doing comparisons, you got to do self joins. So you have to kind of take in like, well, I'm going to grab one product, and I'm going to grab another product, and then I'm going to do these kind of comparisons over those 2. I think that's what you're getting at. So like,
okay, so it's like, yeah.
So that was the hint. So I mean, I think it's going to be. I mean, it's. I don't want to go too far with that. I don't want to answer for you guys. I want you guys to kind of, because it's. I don't know. I mean, what's the benefit of making you guys kind of ride?
I understand that.
But it's like, it seems like I should. I mean, I can do it, but I mean,
Yeah.
Anyways, all right. Well, I'll pause.
So if we just look in more on self join and that.
Yeah, look at self join. You have these comparisons. I don't think I made a point to tell you that you have all these comparison operators. And while we're at it, if you really want to get into it, I'll give you the set operators as well. So if you want to say something like, let's say that we have color here. If you want to say something like color an element of, and then I'll say red, green, or blue. You can do that as well. So I'll give you the set operators, and then and now, since I'm being generous, I'll give you the not element as well. Of course, you can get these, okay. and then also what I'll do is I'll let you kind of group these things and then put like conjunctions, ands, or ors, or nots. Okay, so you can kind of build up expressions there, but that's it. But if I see stuff like this, if I see something like where it's the biggest, price A, that's not going to work. You can't say the biggest there.
Right? Oh, that.
I mean, whatever these things are,
I understand that.
You have to evaluate on whatever the argument, or whatever the tuples are that are being fed into them, right? That's what select does. It'll take a tuple by tuple basis. So that's kind of why the conditions are kind of restricted. So, anyways,
okay.
Great.
Yeah.
We'll be back at 15.
Thank you for the answer.
Yeah, no problem. Okay, there we are. Okay, resume recording. And then what can you guys see? This really bugs because I don't really see what just happened. Okay, first of all, can you guys see the SQL here? Do you see that I have, just someone tell me. Okay, you guys can see the SQL here. Okay, good. All right, and it is recording. It better be recording. Is it telling you guys if it's recording or not? Because if it doesn't record, then I'm going to be screwed here. Okay, it is recording. All right, good. All right. Now I just go back to here and I share the screen. And that's the one. Share. Okay, now you guys can see this, right? You can see the screen with SQL on it. All right, I'm assuming. Okay, perfect. Good. All right, sorry for all the wasted time. There was a good question that came up during recitation or during the break about recitations, and I just wanted to clarify it. So when I sent out like a survey for you guys right at the beginning of the course on Cambro, it looked like, I think it probably said it was an exam or something, or a quiz. But anyways, that was just to test if people can go ahead and answer those, because that's how you're going to actually answer the questions of what you can do. So we're going to, I think on Wednesday or something, we're going to put out a claim sheet on Cambro, and there's going to be 2 of them. They're going to be sent to you, and you can pick which one you want. If you based on, are you going to go to Klaas's session or to my session? So it'll be basically Michael recitation 1 or Klaas recitation 1, and just go into that document and then make the claims on which of the 10 problems you can do. All right, that's, and then once we start recitations, we're going to say, okay, is everybody done? All right. And then once they're done, and that's clear, then we're going to use that as a basis for calling on people to present. All right. Okay. I hope that's clear. All right, because that's the paperless way of doing it. All right, so let's get back to this now, and we're talking now about getting the tuple calculus to work inside of SQL. So if we just like, this is kind of silly. This right here is just the, this is, what is this equivalent to? This is just equivalent to the projection, like, X dot product name such that it's ranging over products, right? So that's pretty easy, straightforward. So now if we do an exist, we can do an existential quantifier. So give me the product names where the it's a product, and then there's that backward E, and then there's a supplier Y, and then we have the join condition there. So basically, this is basically saying, give us the product names where there exists a supplier from Sweden who's supplying that, where the product's supplier ID is that supplier. Okay. And then, of course, we have the Boolean operators, so you can kind of group things and have ors there. So this is where it's going to be either in supplied by either. This might actually kind of be interesting to evaluate. So what's coming from Norway as well. Okay, so we had to add in, I guess, some other like stuff that wasn't Swedish, but now is from Norway. That looks Norwegian. Okay, as does that. Anything with that kind of symbol in it looks Norwegian. All right. Then let's look. So and then instead of having this or here, you can also use the SQL in set operator here. So that's part of SQL, this in, and then you have just a regular parenthesis, and then you list off the literal values. That this for a tuple to be true here, it has to be equal to one of those literal values. All right. Then we have not exist. Okay, so what is this saying here? So the category names, the category name where it's a category, and not exists a product where the supplier is Sweden. So do people understand what this is? I mean, I can write this out in Tuple Calculus, but do people understand what's being asked for here? It's give me the category names for categories where there does not exist a product for which there exists a supplying from Sweden. So this basically is telling us what are the categories that are not supplied by Sweden, and that should be everything. Definitely, seafood should not be there. Yeah, so it's the other ones here. All right, so finally, what is this thing here? So basically what we have is we're going to have a double not exist here. All right, so what are we asking for here? Can anybody venture what this is asking for? Well, it's saying, give me the employees. Give me the employees for which there does not exist a shipper, for which there does not exist an order that employee was processed with that shipper. All right. So let's rephrase that again. So give me the employees where there does not exist a shipper for which they did not ship. Right. So an employee shipping with a shipper means that's what, when an employee ships with a shipper, that means that there is a record of that employee, an order where that's the employee, and that's the shipper. So for a employee to ship with a shipper, there has to be an order that is that shipper and that employee processing the shipping order, right? So give me the employees where there does not exist a shipper for which the employee did not ship, right? So that's another way of saying, give me the employees that have used all the shippers, right? So for every shipper, there exists a record of that employee using that shipper. All right, does that make sense? All right, so I want to actually kind of delve into that just a little bit more because there's something that I want to kind of, this is kind of a key point that I want you guys to see here. Now, first of all, this double not exists. That is going to give us, that's giving us universal. That's giving us a universal quantification, right? So, because I mean, we can do the manipulate, we can do the kind of transformation here and kind of show how that works. But let me just kind of go over here now and share a different screen, or rather share no screen. Stop share. Okay, so now you guys can see this right here, I assume. So this is actually what the, this is the actual universe, this is the tuple calculus that corresponds to the SQL we were just working with. So it's like, give me the employees where for all shippers, there exists an order where X is the employee. So the employee is the employee processing that order, and the shipper that's being used is this this Y. All right, so this is equivalent to that SQL. Now I want to show you guys one thing here because this comes up a lot, and it's a very easy way for me to mark things wrong. So a lot of times what you'll see is something like this. A lot of times you'll see students that they'll actually write this like this. They'll say for all Y, shipper Y, and there exists Z, and okay, and then the rest of this right here, this all this stuff right here gets repeated down there. Okay, now this is just a fancy way. That's just a fancy way of saying false. Okay, that's just a fancy way of saying false. And I want to show you guys why, because this kind of gets to the heart of some. Once you understand this, I mean, just like division, if you fully understand division and how it gets defined, and if you understand this, you understand tuple calculus to a large extent. All right, so why is this the case? Why is this the case that this is just a fancy way of saying false? Picture is quite blurry. Okay, I'll write this up. All right, so maybe just so that you guys see this, is that better? A little bit? Just so you can kind of take a shot of it. You can take a screenshot and see kind of what I wrote. I'll write bigger on the next one. All right, maybe it's still blurry. Okay. Okay, good. So at least people can kind of, all right. Now I want to show you guys what's going on with this kind of thing, why this would be the case. All right, so let's just say this. Let's just say, first of all, what I want to do here is I want us to really look at kind of what this universal quantifier is doing. So when I say for all Y, and then I say, then I have this implication symbol here. Shipper implies there exists Z. What actually that is, if you remember, so P implies Q is equivalent to not P or Q. All right, that's just what the logical definition, of implication is. All right, and that's actually quite important here. Because what this means then is it means the following. It means not shipper or, and then it's going to be or, let's put that in parentheses, there exists Z, order Z, and dot, dot, dot. Okay, and all the rest of the stuff that was there. Okay, right? That's what it means. So we got rid of that. In some sense, this implication here, this implication symbol, is just syntactic sugar. This is the actual meaning of it. And what this allows us to do is it allows us to look at this here. When we say for all Y here, we really mean for all Y. All right, we mean for all Y. So I always make this example. I'm going to introduce a new table, and it's going to be called pet rock. And it's going to have one tuple, and it's going to be Michael's pet rock. Okay, and it represents, in the world, represents my pet rock, which is little eyes on it. I'm not sure if you guys know what a pet rock is, but there it is. There's a pet rock. All right. So when I say for all y here, when I say for all y, I'm not just talking about shippers here. I'm talking about everything, including pet rocks. So this expression here, under the for all y here, this has to be true for every object in the universe, including pet rocks, including orders, including customers, including everything. And so the reason why that's the case is, the question is this expression here true for my pet rock? Well, is my pet rock not a shipper? It's not a shipper. So it's true, because it's going to be not a shipper, and then it's going to, so the whole expression is going to be true. So when I say for all y here, I'm stipulating that it has to be true for everything. All right. And it is true for everything that are pet rocks, that are orders, that are products. But if it happens to be a shipper, right, that goes into the for all y, then we come over here, and then this has to apply. So then basically, once a shipper is in here, then we have to find that there's an order for the particular employee where the employee's shipping with that shipper. Right? I hope that makes sense. But this is really kind of getting down to the nitty gritty of what for all is. So when I see students do this, when I see students say, all right, for all x, and then whatever they put in here, if it's a conjunction, right? It doesn't really matter what it is. If it's just a conjunction, there's no disjunction or no implication, then I will basically throw my pet rock into this. So in comes the rock with little eyes on it, right? It's kind of like clumpy. It looks like a rock, right? The rock is going to land in there, and I'm going to make it false. Okay. So when you say for all x, I'm always thinking my pet rock can also be included as and it has to be true for my pet rock as well, right? So if it's a pure conjunction, I can just throw a rock at it, and it's going to make it false, right? So if it's pure conjunction, then it's false by definition. All right. Okay, I mean, it might confuse you a little bit, but if you kind of meditate on it, it might help to get kind of a full understanding what universal means. All right. Okay, so now, if there's any questions about that, I'll take them, but I don't see any questions. All right. What I'll do now is I'll just continue on with sharing screen. So share screen. All right, there we are, share. Okay, so now we should be back to the SQL. All right, so these are the, did we ever do this? Oh yeah, so we basically say these are the these are the employees who ship with every shipper. Let's just wind up evaluating that and see if we get any employees. Yeah, so it looks like maybe all of them have used all the different shippers. Let's see, is that true? Probably. Yeah. Okay. But you have to trust that it works. This universal actually comes in quite handy for a lot of things. Just to kind of make it practical, you say, why would anybody ever do something like that? It doesn't make much sense. Well, like simple examples like the following. Like, let's say we have a bunch of foods, and then we have recipes, and we have foods that are in stock in a database that's recording the number of, it's recording all the recipes and what foods they need, and it's also recording all the foods that we have in stock. Well, the recipes that we can make are based on the universal. So basically, it's like, give me all the recipes for which all the foods that the recipe requires are in stock, right? So you will get, and that applies to a lot of things other than recipes. It applies to any kind of action that requires a bunch of objects being present or something like that, right? So it's a very general kind of property that applications need. So universal comes up quite a bit in practice. All right, let's see here. So let's go on here. All right. And again, universals come up a lot in practice, but for you to get it to work with SQL, you're going to have to use a double not exists, because there is no universal in SQL. All right, so let's go on here. So now let's go to what I call like syntactic sugar over SQL. So what we see here is we see something like this. All right, so look at this right here. This is this is actually not really such a great idea to do it this way, but let's just show here. What you can do here is you can basically say where a value, and then you can, you can't really do this in Tuple Calculus, I'm sorry, in relational algebra, not the way we've been doing it, but but you can do it in SQL. So it's a little bit, it's not just sugar, actually, this is a little bit beyond. But basically what it's doing here is doing a subquery here where it's getting the city where the company name equals Mason Dewey. And then it's basically saying, give me the suppliers where the city equals that. This is not good practice. This is not very a good way of doing the query. And then likewise here with the, where the, all right, this, okay, company name equals that from customers, right. Okay, so this right here, notice here that this, this will work. But notice that it's a little bit junky, and I'll explain to you why, and this is kind of important to, all right, there are none of them, that's nice. I would have assumed that I made it so there was one. Mason Dewey. Here, let's see what's wrong with this. Customer name. This is getting out the city, I guess, of Mason Dewey. Okay, so that's where it is, Bruxelles. All right, I don't want to trick around this too much. The idea then here is that what's coming back here is this Bruxelles or whatever, and then there's no company name in then Bruxelles. And what this right here is doing, this actually this should return us with null. So this basically should be where the city is null, I imagine. So let's see what happens here. Yeah, so you know, I should trick around with this so I get a city that matches there. But look at this right here. So this is the same thing, but now I'm basically the subquery here is like where the city, where it's just gonna get all the cities from customers. So if you think about this, this actually doesn't make any sense. This doesn't make type sense because this is a single attribute here, right? A single value rather coming. When I grab a suppliers, I'll get a single value here. When I grab this, I'm gonna get a set or a set of values. All right, and so basically what if we do it that way, then this should actually boink. So this returned in a runtime error. All right, so SQL is not a very strongly typed. I mean, these things are kind of risky because what this means then, it means, let's say hypothetically that you had right here, there's nothing that says you can't have two companies with the same name. So if you had a query like this in your system and you were always assuming, oh, it'll always be one city that comes back because, you know, if I have a company named Acme, it's always going to be in one particular city. But let's say there are two companies named Acme, then it's going to return two cities here, you know, and they're in distinct cities, and that's going to crash your query. So this right here, you have this kind of type vulnerability here if you kind of do with these kind of things in SQL. So don't do that. So generally speaking, get away from those kind of things. You have in here. This is a little bit better. And notice with the in here, we can have tuple inclusion. So these are pairs here. So it's a little bit more than just single. I mean, the easy one would be just if it's just like a single value here, but you can put tuples in there as well. So this right here, you can put like subqueries here in the set specifiers here. So this actually should work. All right. So these are kind of sugary things that are kind of beyond what yes, it works. That were beyond kind of the tuple calculus relational algebra that we were doing, but they're not really increasing the expressivity of the language. All right, but what they are is they're just kind of okay. So you can say not in, and then you can say stuff like any. Okay, so any basically this means that it's kind of it's going to search through this and it's going to find if any. It's kind of like there exists. I tend to kind of be against these things. I mean, I avoid these. I've never really had a good reason to use these things in practice. I always found it kind of more elementary or fundamental way to express things, and that's also true with this all here. So this right here, basically, this is not a universal quantification. This is basically just saying that it's like doing a max. So with give me the unit price is greater than all of the unit prices from some set here. So in other words, this will only be true if I look at all of these, this unit price is always greater than or equal to that. All right. So usually there's a better way of doing that. What's the difference between capitalized keywords and those in lowercase? There is no difference. So SQL is the keywords in SQL are type or case insensitive. It's good conventions though to keep them capitalized. You want to have some way to make. I mean, SQL is a really kind of ugly language in the sense that, I mean, if you really want to have some kind of conventions over how you write stuff, because it'll just be. I mean, there's a certain taste that you have as a developer. You want to make sure your names. You want to keep things consistent, and it just kind of, you know, you have less wear and tear on your attention if you do it that way. Another thing also to keep in mind. Now, not all SQLs are like this, but a lot of them are, and that is that do not name a table select. Don't do it. And don't. So in other words, the big keywords in SQL, don't name attributes or tables based on those. When you define a database, do not name the tables or the attributes based on SQL keywords. So this happens all the time, right? Somebody will have like, I'll name this attribute select. All right. So why is everything kind of all, you know, a lot of these, they don't have a good sense of namespaces in SQL. I mean, you can put schema, somebody could say, well, you can do it and blah, blah, blah. Here's what you do. You have to kind of specify the schema, but just don't do it. Or if you have to do it, like I think the one that usually happens is from. So a lot of people will say, oh, I want to have an attribute called, you know, to, and I want to have an attribute called from. And then they put the attribute name from, and then based on the SQL engine, it's like everything's like, it doesn't really, it'll give you some kind of cryptic error message. You don't know like why. So it's like Python, whatever, you put it like prepend it with an underscore or append an underscore to it, prepend or append an underscore so you can kind of get it so you're not clashing with SQL reserved words. All right. Order is also another one. So people will say like, do you want to call it attribute order? Well, all right, do that and then see what happens. I mean, it's gonna, yeah, stay away from the SQL keywords. They're reserved. All right, but they are they are case insensitive, and so are the table names. By the way, I could say this products. I could say this, right? I could say that. These are all the same. All right, so it's case insensitive. All right, so where were we then? All right, so that was just kind of a little bit of sugar like you can add to. Now let's go a little bit beyond. So now we're getting into the kind of the realm of going beyond the expressivity. We're going beyond what you can express in the basic relational algebra tuple calculus. But of course we have to do this, right? Because these are such basic things. So counting. So this right here, you cannot do this in basic relational algebra. You can't do counts, okay? So, but we can do it here, right? 77 of them. All right, so count over the product name. So what this has done actually, I mean, it sounds, I mean, you could make this kind of more glamorous by saying the following, that is that SQL, so tuple calculation relational algebra are based on first order, you know, the basic first order logic, right? You know, and even that you would argue, you know, that they're a little bit beyond. They have things like these built-in predicates, like less than, greater than, and they have this kind of. They're bringing a lot of other stuff in that the basic first order logic doesn't have, but or you have to extend it to get it to have. But they're fairly straightforward extensions. But the thing is that when you get to stuff like counting the number of elements, you're going into higher order logic, right? So you're going into like and it's not even second order logic. It gets beyond that. So very quickly, what happens is the expressivity of SQL becomes something that's mathematically very, very difficult to deal with. All right. Now, there was always going to be a tension between the theoreticians and the mathematicians, these types, and the practical people who want to get the work done. You need to have higher order stuff. You need to be able to count the number of elements in a set, right? That's just the way it is. I mean, they're not doing SQL because they want to, you know, do math. It's not like a mathematics contest. It's not like, you know, who can prove things about it. It's they got to get work done. All right. So you have stuff like this. So you're doing counting, right? Also ordering. So you have the idea of doing ordering. So basically, right here, like we had this idea. Well, not only that, we had this idea of doing like arithmetic inside inside the select clause or inside the projection. So we have the arithmetic going on here. We have the product name. We take the unit price times the current units in stock. I guess that's kind of the expected revenue for the products. So what we do here is we do this. So notice you can't do this in the traditional relational algebra unless well, could you do this in the traditional? So you talk to some mathematician and say, well, and the mathematician says, oh, yes, but you can, because all you have to do is define like a multiplication table, right? So you'd have to have an extra table that defines multiplication of all. I guess these are probably going to be up to a certain precision. So, but that's impractical, right? I mean, but yeah, you could do it. Like if you wanted to have this, where you wanted to have the product of these two, and then you could bring in another table where you joined based on the unit price, like the unit price equals X, the units in stock equals Y, and then Z is the result in that pre-computed kind of table. But that's getting ridiculous, right? I mean, that's kind of beyond, that's kind of laughable. All right, so I mean, this is kind of moving beyond the expressivity of your traditional relational algebra. All right, and then ordering certainly is going to be an issue, right? The ordering, I don't even know how you could kind of rig that in, but ordering. So now we're ordering on the value here. Again, very practical, but if somebody wants to sit there and kind of like start proving things about SQL, this is going to make things really hard, right? So the mathematicians should be like, okay, a question in recitation wants you to name all the teachers who teach more than one course. How could you do this without counting the amount of rows and checking greater than one? You know, the thing about that is that it's like, I want you guys to kind of struggle with the relational algebra. The relational algebra is like, you ever seen those little poodles that kind of like, they put like a little dress on the poodle, and then it kind of jumps up, and then you can dance with it a little bit. It's almost like a dancer, but it's like a poodle, like a dog. That's what the relational algebra is. So you can actually get that little poodle to answer that kind of question, right? So you can, and in doing it, I think you'll kind of learn the relational algebra better. So it is doable. I will say that. The question was, how can you do this? Sorry. The question is, in recitation, you want to name all the teachers who teach more than one course. How can you do this without counting the amount of rows and checking greater than one? And I'm saying you can, just using kind of the basic relational algebra. All right. Okay. So let's move on here. I mean, you know, it's actually we're not even to a point now where we're going to get to a point where we can answer this with an extended relational algebra or SQL. We haven't even really got into how we can answer this with SQL. So, but we'll get to that. You'll find it's a lot easier when you have a higher order language. All right. Let's see here. Right. So order by ascending, descending. These are some keywords here. What do we have? Oh yeah, this is not so. You can do kind of like pattern matching in the conditions. So, you know, this is a really old way. SQL, when you use the like operator in SQL, it's using this really old-fashioned way where basically anything with ALE in it, so this is any arbitrary number of characters, this is any arbitrary character. So anything that will be like any kind of ALE, it looks like. Let's see here. So I don't know what they had for different ALE types here, but let's just see. Sasquatch ALE. Sasquatch ALE matches because if that Sasquatch space is matching this part, and then you have ALE, and then this right here is matching nothing. Okay, that's so you have that kind of stuff that goes on in SQL. This is a little bit beyond. But the thing about that is that just to keep in mind, later on, what you want to do is you want to use a regular expression. So the SQL has this using it this way. Well, sometimes you use it this way because it's so easy. But strictly speaking, there's a whole new regular expression processor inside of SQL. So they don't do it the old-fashioned way anymore. Of course, a lot of them are different. So you get different idiosyncrasies based on the SQL engine you're using. So yeah, this will always work across engines. All right. Yeah. All right. So I think that basically was what I wanted to show, just kind of using the Northwind thing. So the zip file is up there. You can download this and you can kind of make all this work on your own if you want to. Okay. All right. So now let's go back to the slides. And we're not going to finish everything today, but that's fine because we have some slack kind of built into the schedule. All right. So now. All right, so we'll just kind of quickly go over this. Yeah, so I was just talking about those the set semantics for set operators in SQL. I think I've already said all this. All right, so if you remember these from the lecture 1, what was the difference between this? This was doing a Cartesian product and then doing equality. Whereas this guy right here, he's actually just grabbing and turning this into a set. So he's selecting B from S. So he's turning this into a set right here and then walking each tuple in R. So this will result in fewer A's get produced. So this is the example that's going on here. So this will give us two twos here, I guess, or select B. Yeah, select B from S. This gives us two twos because it's based on a bag semantics. So we get 2 and 2 here because we're taking this from S. But that's a set, so that's 2 and 2, right? And then all it's going to do here is it's going to walk R, right? So it goes here and it says, is 2 in that set? Yes. Right, then it's going to say, is 3 in that set? No. All right. So then it's just going to give you B as a result. Okay. So, but if you do the join, it will do the Cartesian product and it'll walk both of those, and it's going to wind up giving you back. It's going to wind up giving you back the select A. It's going to double it. It's going to go over. Let's see, 2 and 2. So it's going to give you 1. Is that right? Yeah. Anyways, I mean, I hope you guys see it. Don't get too much of that, but we're going to try to make a little progress here. Okay. So, so now this is we're going to try to kind of get into this business of now. Okay. Now we've shown a little bit of SQL going beyond Tuple Calculus a little bit, but what we're going to do now is we're going to go back down to the relational algebra, and we're going to kind of make the relational algebra extended. Okay, we're going to extend the relational algebra. So the here are the operations we're going to include in the extended relational algebra. The delta operator, which eliminates duplicates, right, from bags, right, because we want to everything when we go to extended relational algebra, everything's based on bag semantics now. Okay, we're just dealing with bags. All right, we're going to do sorting. All right, so we have the tau operator, which does sorting, and then we're also going to have the gamma operator, which does grouping. Right, and then we'll see aggregation as well. Finally, there's an issue of what's called an outer join, which is a way to basically keep around can you keep around the tuples that don't make it through a join, right? So because a lot of times, and then what we're going to do is we're going to pad out with null for those. So that's another example actually of how nulls are being used. They can be the result of a outer join. All right, so this delta operator is really trivial. This is a duplicate and eliminate. So basically, it'll turn it back into a set. So right, this is going to correspond to that distinct. Remember, distinct in SQL. Each of these is going to have some correspondence into SQL. There's not going to be any correspondence into Tuple Calculus because now we're basically just leaving Tuple Calculus behind. Tuple Calculus is no longer. I mean, we can sit there, we can try to come up with like a higher order syntax, but that's just that's really hard. I mean, people have tried that, but it's really kind of a difficult thing to try. It's very difficult to extend the syntax around Tuple Calculus to get a higher order to capture all this stuff. We're just going to go over to SQL. All right, so this basically is going to correspond to distinct in SQL. All right, so duplicate elimination is pretty easy. If you here's the relation, right? So all of these relational algebra, extended relational algebra operators, or I shouldn't say all of them, but most of them, the vast majority of them, take in a relation and give you back out a relation, right? They stay in the algebraic sense, but that's not completely true, and we'll see that in a second. So yeah, so in comes a relation into the delta operator. All right, so R comes in, boink, 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 but all it's gonna yield up here then is the set, right? So it's gonna make them distinct. Right, so that should be clear. That's delta. Okay, now sorting. Sorting, technically speaking, sorting does not return a relation. All right, you shove in a relation and you get out something different. You get out something that's basically a sorted relation, right? So a relation has an ordering inside of it, right? So that's the one that kind of violates the notion of staying relational algebraic. But what are we supposed to do? You know, do we want to have sorting? Do we want to go to the programmers and go to the people who are buying this stuff and say, no, we can't, because this is violating the whole notion of an algebraic scheme, we can't give you sorting. They'll laugh at us and say, who can, because that's who we're going to pay. They don't care, right? So we're going to have sorting. All right, and sorting is done with the tau. All right, so you basically list a set of attributes of R2 here in the tau operator, and it's going to break the ties arbitrarily. And the result is going to be, it's neither a bag nor a relation, it's a sorted relation. So basically, here's R, 1, 2, 3, 4, 5, 2. And then we do the tau operator where we're sorting on B, all right? And then one of the so basically 2 and then 4, right? So we're sorting in ascending order on B, right? So basically it'll grab that one, no, it grabs this one arbitrarily first, and then it's going to grab that one, and then it's going to grab that one, okay? And that's doing the sort there. What if we want to do sort on B descending rather than ascending? So we want to put the top B first. Well, there's a trick. You just put a negative symbol, negative sign on B here, all right? So that would do it. Okay. Yeah, all right. They're sorting. So sorting is a tau operator. All right, now we're going to get to the aggregation operators. These are the ones that where we're really going to increase the power. All right, so aggregation operators are not operators of relational algebra at all. All right, so they can apply to the entire columns of a table and produce a single result. Okay, rather they apply to the entire columns of the table and produce a single result. That's not really the best way I would put it, but the way I did put it for some reason. The most important examples are sum, average, count, min, and max. Okay, so these are the aggregate operators: sum, average, count, min, and max. And notice how all of these things, what they're doing is they're taking in, maybe this is what I was trying to get to, rather they apply to an entire column of a table. Okay, it's going to basically give you a vector of values. So if I put in 1, 2, 7, that is the kind of thing that can go into a sum, or an average, or a count. There's 3 of them. A min, that'd be 1. A max, that'd be 7. Sum would be just, 10. The average, well, what is the average? 3.33. Okay. But you notice here, so what it's going to do is it's going to basically return to you then a single value, right? So a val. So it's going to give you a scalar, right? So basically these are vector to scalar operations. That's what aggregate operators do, okay? So just think, so are there other ones that you could have? Sure. But unfortunately they don't really, it's a lot of times they don't include them. So you have to kind of cook them up yourself, like median. Median, actually, something, this is for everybody to know, right? I mean, the difference between, this is not, this is much statistics we're going to get in the class. Average and median. Please compare average and median. That's one of the most important things you need to do in any kind of reporting. What's the average and median, and maybe the mins and maxes to get the outliers. Yeah, median is a lot of times a lot more useful than an average. All right, right. Okay. Yeah, so those are the aggregate operators. So we see, again, they're taking in a vector and they're giving you out a scalar, right? Okay, so how are we going to apply this in something that's extended relational algebra? Well, we have to do this via the gamma operator, which is what's called a grouping operator. Okay, so basically the way it works is this: is that when we have L is going to be a list. So basically, we're going to say take a relation R2. And we're going to feed that into this gamma, or we're going to feed it into what I call the grouper. All right. So we're going to have a grouper. And what does a grouper do other than group? A grouper groups. It's going to group the tuples. It's going to basically wind up defining a set of different individual groups that are going to be defined or pulled out of the table. So we have these individual grouping attributes, and then we're going to have these actual aggregate functions. And the aggregate functions then basically are something that applies over an attribute. Okay, and so and then an arrow is going to rename this component. So let's give an example here, because I think this will make things a lot clearer. All right, so we're going to do a grouping. So here's our relation here. Okay, A, B, and C, and we're going to basically do. I could add another one in here, but let's just keep it simple here. We're basically going to do a grouping, and this is a grouping attribute A. This is a grouping attribute B, and this is a aggregate operator C. Okay, so now when we do the groups, so now we're gonna take the grouping attributes A and B, okay, and using A and B, we're gonna group this relation here. So for distinct A-B combinations, we have 1, 2, and then we have 1, 2, but those are just part of the same group, right? That's the 1, 2 group, and then we have another group, the 4, 5. So we basically are going. Our grouper is going to form 2 groups, right? So the first group is the group. Okay, so we have one of the groups is, I'll just kind of represent it this way. One of the groups, I don't know. Anyways, one of the groups is going to be 1, 2, 3, 1, 2, 5, and then another one of the groups is going to be 4, 5, 6. Right? If I had another tuple here, let's say I had another tuple. 4, 5, 7, that would be added to this group, right? If I had another one, 1, 3, 6, that would define a new group called 1, 3, and then it would have 1, 3, 6. But let's just stick with this here. Hope that's clear. So we have 2 groups. We form 2 groups. Okay. Now we also have right here the average C. All right. So the average C. Now that's going to apply to this column here, so to the C values for. To the C values in each of these groups. All right, so so this is going to basically define this vector here, 3, 5. So that's going to go into average, and that's going to give us out a 4, right? So the result of this is going to be 1, 2, 4. And then the result of this is going to be, well, it's going to be the average of that. So it's going to take in this vector here, which is just a singleton or single value. And it's going to give us out a 6. So 4, 5, 6. Okay, so there we are. And 4, 5, 6. There's the 2 groups, right? And then here's the result: 1, 2, 4, yeah, 4, 5, 6. Yeah. So there's the result. So that's really the basis of it, right? So I hope that is kind of clear. So what's coming out of this is a relation. So relation comes in, right? And then you do the grouping on the grouping attributes, and then you do a calculation of the aggregate operator on the on the column that is remaining inside the groups, right? So that column will then determines the vector, because you can have multiple elements in the group. All right. So let's see. So again, these are some of the average ones. Count also does counts the number of tuples. So in this case here, if we had count instead of average, then the result would have been 1, 2, 2, and 4, 5, 1. Right? Okay. So those are now. That's not an example of it. Let's not get to yeah. So these other things here, we've gone over time anyways now. We'll finish the rest of this next time. So we're not too far behind. But are there any questions or anything? I just that gamma operator was an important one. That's the one that can be a little tricky. But hopefully I explained it in a simple enough manner so you can see the basis of it. But you'll see that it can be a little tricky when we go over to SQL. But yeah. Yeah, because there's a question here. Are we supposed to do the recitation solo, or can we work it with them in groups? Yeah, go ahead and work in groups. It's fine. But when you get called upon, it's you. So I'm not going to call on a group. It's going to be when you make the claim. It means that if you get called on, then you have something to say. But being wrong actually is kind of. I encourage students to actually be wrong on recitation, because it'll make it more interesting discussions. If everybody gets it right, it's kind of going to be a little bit boring. So getting it wrong is not a problem at all. It's I never. If it's clear that you never even looked at the problem, then I'll be like, then it'll be a little bit of an issue. But Yeah, so in recitation, how to do the presentation? Well, you get called on, and then I say, all right, problem number 4B or whatever it might be. And then I say, okay, let's say whatever the name is, take it away. And then you turn your microphone on, I turn mine off, and then we hear you kind of describe how you approach the problem and what you present as a result and stuff. Yeah, you're supposed to kind of do this on paper and then drop it in Canva. The reason for that is that we want to have at least one kind of sanity check if we want to ever go back and look to make sure the students were actually doing the work. But you'll get the credit. I mean, you're going to get the credit if you get claimed. If you make a claim and you don't get called on, you get the credit. But you understand you were taking a risk. You're sticking your neck out there. It didn't happen that you got called on, but you could have been. All right, let's see what else we have. Any other getting things wrong? Getting things wrong will not. Yeah, that's right. Yeah, as long as you do things wrong in an interesting way, then it'll stimulate discussion. Yeah, I think it's actually good to be wrong. I think that people need to kind of practice being wrong. I mean, don't quote me on that, even though this is being recorded. I mean, it's because it's good just to I mean, that's what all these entrepreneur types say, right? They say that it's important to fail and to learn things, right? So not to, you'll never get anything wrong if you don't try, right? And that's what we want to avoid. We want people to actually experience life and to do. All right. Let's see. Are we supposed to open? Yeah. You can handwrite it and then just scan it. It's fine. It's not. You're going to be claiming, so there's like 10 problems on recitation 1, and so you're going to have a chance to do individual claims for each of those. So based on that, like if you claim like 7 of them, then you're going to get 70, I'm sorry, you're going to get, it's not 70, you're going to get 35 points. I guess each of them worth 50. You're going to get an email. So for those people who did not ever get an invitation to that first little survey I gave, that would be a problem. So send me an email if you did not get that invitation. I mean, some people who kind of maybe registered late or didn't get it, but the issue is that everybody's supposed to get it. So if it's Thursday morning and you still haven't got the invitation to do the claim, then send me an email. Yeah, email went out. This was way in the beginning of the course. Let's see. Any more questions? But don't stress about recitation 1. I mean, again, it's just the important thing is that you have a chance to do your claims, and then yeah. All right, everyone. Okay, so I think that so next Monday we're going to continue with lecture, but Thursday, of course, we have recitation. So yeah. Are there any more questions? Or I'll post this to up to well, on Canva, the recording. So. Okay, so well, I mean, if people don't get it by first of all, this is a good time to make sure that you're registered for the course. All right, that you're getting Cambro. If I send if I send an email out to Cambro, I'll send one right now. I'll send an email right now to Cambro this minute, and I'll say, hello, just if you didn't get this email, then so I'll tell you, I promise I will send this email out now. And if you don't get the email, then that's a problem. You need to kind of get yourself registered, because otherwise you won't get the claim form. Yeah. Okay, that initial survey is closed now, so you can't go into it now. It's closed because there's a certain duration, and we're going to close these claims as well on recitation. So they'll close like about 10 minutes into recitation, 15 minutes into recitation. And also, by the way, if you basically make a bunch of claims and then when we call on you, we get a silence. If that happens, then you're going to get a 0 on the recitation, and you'll also be on a list that means that you're going to get called on, definitely get called on in the future. All right, so don't do that. That sometimes happens, especially in these Zoom times. Is somebody will go in, they'll make all the claims, and then I call on them because it just happens to happen that they get selected, and there's crickets, and that's not good. So don't do that. That actually happened somewhat recently, and yeah, that's not a good thing. So you definitely got to be there for it. No, you lose no points if you're wrong. The only way you lose points is if you but no one ever does this where they kind of like, oh yeah, I claimed I could do it, but I haven't even looked. What was the problem again? I never even looked at this. That's, but no one does that. No, you cannot. Look at that survey. Forget that survey. I can even just delete the thing. That was just a way to kind of verify that things were working. But you're going to get a chance to make a claim. We're going to put it out on Wednesday night or Wednesday afternoon, and then at that point you're going to make your claims, and that'll be that. You can wait till the next morning to do the claims, but don't stress. I mean, this should work. We'll and once you see this, it'll be, yeah, it'll be simple. Okay, are there any more questions? All right. Okay, well, with that, I bid you all goodbye, and I'll see you on Thursday. Or I'll see half of you on Thursday. Other half will see class. Okay, see you all later.